So far we had studied about ray optics or geometrical optics, in which we treated light as rays which were passing through lenses, which were getting reflected through mirrors. Now in this chapter we'll go down to the microscopic level. We are now going to study wave optics. The first phenomenon we're going to study in wave optics is the interference of light waves. We'll study what happens when two light waves coming from the same source interfere like this. And we focus those two light waves on a screen. What happens then? We'll study about the Young's double slit experiment. A lot of interesting things are going to follow. So let's begin with interference. First of all, let's try to understand the concept of optical path. Let's say there's a point A and a point B. Then the distance traveled by light when it travels from A to B in vacuum is called the optical path of light. So basically, if there are any 2 points and if light is traveling from one point to another in vacuum, then the net distance that it travels will be called the optical path. Let's see how this differs from the actual path that we see. Sometimes you see the optical path is different from the distance between 2 points. Let's see how that happens. Let's say there is this source and there is this destination, and both of them are separated by a distance L. So when light travels from the source to destination in vacuum, clearly the optical path will be L. Now suppose a glass slab of refractive index mu and thickness T is placed in between the source and the destination. What will the optical path be in this case? The optical path in this case will be the distance traveled by light in vacuum in the time that the light takes to travel from the source to the destination. In the first case, the optical path was L. In the second case, the optical path, I'll repeat, is the distance traveled by light in vacuum in the same time, in which the light travels from the source to the destination when there is a block of refractive index mu in the path. So what will this distance be? This distance will be the speed of light in vacuum into the time taken by light to travel from the source to the destination when this block is placed in the path of light. So you can see that the time taken by the light to travel from source to destination will be L minus T divided by C, because the light travels the distance L minus T with the same speed C in vacuum, plus T divided by C by mu. That's because the light travels the distance T inside this block with a speed C by mu, because the speed of light in any medium of refractive index mu is C divided by mu, where C is the speed of light in vacuum. Hence the optical path, when a block is placed, comes out to be this expression, L plus mu minus 1 into T. The core concept here is that the optical path represents the equivalent distance traveled by light in vacuum in the same time that it is traveling from source to destination in our problem. So the equivalent path in vacuum is L plus mu minus 1 into T. Understood? So the difference in the optical path when a block is placed and when a block is not placed, that gives us the path difference or the optical path difference, right? So as you can see, the optical path difference caused by a block of refractive index mu is mu minus 1 into T. Here you go. We already know that if there is a path difference between two light waves, interference occurs. Remember, we had studied this in the chapter of waves. We had studied that when two waves, they interfere, maxima and minima are produced. There is one particular point where there's maximum intensity, there's one particular point where there's minimum intensity. The yellow portion that you see on your screen here, it represents the variation in amplitude of the waves. The final wave, which is formed when two waves interfere is something like this, So as you can see, maximum intensity, minimum intensity, and so on. And it is this interference between light waves when there is a path difference between the two light waves is what we're going to talk about in this chapter. So let's produce interference in a different way. Earlier we placed, a block in the path of one of the light waves and we created a path difference between two light waves. Now let's take, two different sources. As you can clearly see, the light wave coming from this source, is traveling a lesser distance than the light wave coming from this source, and therefore, these two waves can interfere to create a pattern on the screen. The pattern will be something like this, where both the waves interfere constructively, there will be a maxima. Where both the waves interfere destructively, there will be a minima. And in the middle portion, the pattern on the screen will gradually vary from a maxima to a minimum, right? But the interesting phenomenon is that, when we actually place two light sources, the way we're showing this on your computer, an interference pattern is not obtained. That's weird, isn't it? But that is true. Two different sources do not produce interference. What is the reason for that? After all, we studied in the chapter of waves that two waves with a path difference between them, they'll produce a maxima minima pattern. So why not? The reason is that it is very, very, very difficult to produce two light waves of the same frequency. And if there are light waves of different frequency, in that case there will be no interference pattern.